Okay, next I will create a table for this game and find the mixed strategy Nash equilibrium. If you want to do it yourself, you can read it and try it. Just make the officer player 1 and the dealer player 2. And this is the rest of the story. Okay, so this is the setup. Without disruption by police, 100 trades will occur. The dealer's payoff equals the number of trades he consummates. For the officer, her payoff is the number of trades she disrupts. Okay, so if they are both in the park, then only 40 trades occur, which means that 60 are disrupted. If the drug dealer is in the park, but the officer is out on the streets, 100 drug deals go down. If the officer is patrolling the streets and the dealer is out on the street corner, then only 20 trades occur. And if the dealer is on a street corner but the officer is in the park, 90 trades occur. Okay, so as I said, the police officer will be player 1, the drug dealer will be player 2, and the strategy for each of them is street corner or park. So if both are on the street corner, what did we say? If the officer is patrolling the streets and the dealer is out on the street corner, 20 trades occur. So that means the police officer has a payoff of 80 and the drug dealer has a payoff of 20. Let's see. If they both end up in the park, 40 trades occur, 60 are disrupted. So the police officer's payoff is 60, 40 for the drug dealer. Drug dealer is in the park, but the officer is on the streets. Then 100 trades occur. So that's going to be 0 for the officer, 100 for the drug dealer. And if the dealer is on the street corner, but the officer is in the park, then 90 trades occur. So 10 get disrupted, but 90 happen. All right, so like we did before, we want a probability for the drug dealer being on the street corner, and a probability for him being in the park, and a probability for the police officer being on the street corner, and probability for her being in the park. Okay, so we'll say the expected utility for the police officer being on the street corner is S sub P, and for being in the park is P sub P. Okay, and for the dealer, we want the expected utility of being on the street and the expected utility of being in the park. Okay, so expected utility for the police officer being on the street corner is going to be P times 80 and 1 minus P times 0. And the expected utility of being in the park is going to be P times 10 and 1 minus P times 60. Okay, so let's see. We have 80p plus, that will all be 0, and 10p plus 60 minus 60p. So 80p equals 60 minus 50p If we add 50p to both sides, we have 130p. If we divide both sides by 130, then p equals 6/13. Okay, so the drug dealer wants to be on the street corner 6/13 of the time, and in the park 7/13 of the time. Okay, so this is the officer's strategy, first one, and then the second one is the dealer's. So we just found that the dealer is going to play the street, beyond the street, 6/13 of the time, and in the park, 7/13 of the time. Okay, and then the probabilities that the police officer is going to set will be Q and 1 minus Q, so that the expected utility of the street corner and the park are the same for the drug dealer. So let's see. So the expected utility for the street corner for the drug dealer is Q times 20 and 1 minus Q times 90. And for the park, it's going to be Q times 100 and 1 minus Q times 40. Okay, so let's see. We have 20Q plus 90 minus 90Q equals 100Q plus 40 minus 40Q. So that's going to become 90 minus 70Q equals 60Q plus 40. Okay, so we'll add 70Q to both sides. That gives us 90, 130Q again, plus 40. Subtract 40 from both sides. So that means we have 130Q equals 50. So Q equals 50 over 130, 5/13. Okay, so the police officer is going to want to be on the street corner 5/13 of the time, and in the park 8/13 of the time. Okay, so the mixed strategy Nash equilibrium is 5/13 street and 8/13 park for the officer, and as we said, 6/13 street and 7/13 street for the dealer. Okay, so they'll need a 13-sided die, or two of them, I guess. All right.